Welcome to section 3.6, related rates. Our goal today is to solve problems that involve related rates. The procedure that we'll be following is first, sketch a figure if possible. Next, identify all relevant variables, including those rates that are given and the ones that need to be found. We'll express all of our rates as derivatives, whether they're given to us or we are looking for them. Find an equation to connect our variables, and then implicitly differentiate our equation. We'll use our chain rule and any other properties that we have learned about so far. Once we have differentiated, we can substitute in any values we've been given and then solve for the derivative that will give us the unknown rate. This process is generally what we'll use every time. Of course, with different scenarios, we may have a few different steps. So let's get started. Assume that x is x of t and y is y of t. Find dy dt, so the derivative of y with respect to t, given 3x squared plus 9xy minus 2y cubed equals 15. They're giving us dx dt, so the derivative of x with respect to t is 4, x is 2, and y is 1. So, first, let's find the first derivative using implicit differentiation. So we were given 3x squared plus 9xy minus 2y cubed equals 15. If we take the derivative, then 3x squared is 6x, and then the derivative of x, dx dt, using our chain rule, plus 9xy. So now we have a product. So we'll take the first 9x times the derivative of the second, dy dt, plus the second times the derivative of the first, 9 dx dt, minus 2y cubed. So we'll have 6y squared, derivative of y, dy dt, and the derivative of 15, 0. So we needed to use the chain rule on every single term because we have x and we have y, but we're taking our derivative with respect to t. So don't forget your chain rule. Now we'll substitute in all of our known values and we'll be able to solve for dy dt because that's what we're looking for. So it gives us dx dt. So first, well, I guess I'll put x is 2, dx dt is 4, 9, x is 2, dy dt is what we're looking for, dy dt, plus y is 1, 9, dx dt, 4, minus 6, y is 1, squared, dy dt equals 0. So we have everything plugged in. So if we multiply these, not that, this one, and add them, we will get 84 in the constant. And then here, the dy dt's, if we multiply and add those ones, we'll have 12 dy dt. So we are combining our like terms here, and we want to solve, so we'll move the 84 over. 12 dy dt, negative 84, divide by 12, and so our dy dt is a negative 7. Okay, next we have an application. A boat is being pulled toward a dock by a rope. If the rope is being pulled in at 5 feet per second and the rope is 3 feet above the dock, how fast is the distance between the dock and the boat decreasing when it is 30 feet from the dock? So let's draw a picture of what we have here. We've got a boat out in the water, and it is tied to a dock. So this is our distance away from the boat to the dock. So I'm going to label that B. And it says that the rope is 3 feet above the dock. So we've got kind of like a little pole here with the rope, and the rope is pulling in the boat. So the height of the rope I'm going to label A, and then the length of our rope I'm going to label C. And the reason I'm doing that is because we have right here a right triangle, sort of. My rope is kind of doing whatever it wants. But we can solve when we have an equation. And when we create our right triangle, we automatically have an equation we can use. So let's label some things. Our height A, we said it's 3 feet above the dock. So our height A is 3. That is not changing. So dA dt, the rate that our A is changing is 0. It's not changing. It's staying there. B is the distance away from the dock. And we said the boat is 30 feet away from the dock. It wants to know how fast is the distance from the dock and the boat decreasing. So we don't know dB dt. That's what we're going to be looking for. C is the length of our rope. And we said that the rope is being pulled in at 5 feet per second. The rope is 3 feet above the dock, and it's decreasing 30 feet from the dock. So our C, we will have to find, but we do know that it's being pulled in at 5 feet per second. dC dt is going to be -5 because it's decreasing, right? They're pulling it in, so the amount of rope is decreasing by 5 every second. Okay. It's going to be dB dt and C that we need to fill in. In our case, we can fill in C quite easily because we know the Pythagorean theorem. A squared plus B squared equals C squared. And so that is one value that, although it's unknown right now, we can find it. So a squared, 3 squared, b squared, 30 squared, equals c squared. So we have 9 plus 900 equals c squared. C, we're just going to take an approximation after we add and square root 30.15. Okay, so I'm going to update what we know. C is approximately 30.15. Okay. Now we have one unknown left, and that's the one that we need to answer our question. So, what I'm going to do is I'm going to continue to use the Pythagorean theorem because look at it. We have A, B, and C, and if we take the derivative, if we implicitly differentiate, we will also have dA dt, dB dt, and dC dt. So it will give us all the variables that we need and hopefully make it nice to solve. So we have a squared plus b squared equals c squared. Taking the derivative of a squared, we will have 2a, chain rule says dA dt, plus the derivative of b squared, 2b, and chain rule, dB dt. Derivative of c squared, 2c, and chain rule, dC dt. Now we can plug in everything that we know. 2a is 3, dA dt is 0, 2b is 30, dB dt is what we're looking for, so we'll leave it. 2c is 30.15, dC dt, -5. This is all 0, so we've got 60 dB dt equals, this multiplication will give us -301.496. And if we divide our 60 off, this will give us dB dt of -5.02. And so we will say the boat's distance from the dock is decreasing at a rate of about 5.02 feet per second, because we don't want to forget our units, especially in an application. A 30-foot ladder is placed against a vertical wall. Suppose that the top of the ladder slides down the wall at a constant rate of 3 feet per second. How fast is the bottom of the ladder sliding away from the wall when the top of the ladder is 15 feet above the ground? Okay, so we've got a wall, and there's a ladder. And the ground. So, again, we have a triangle forming. We'll label our height of the ladder A. We'll label the distance from the bottom of the ladder to the wall, our B, and we'll label the length of the ladder C. Just to highlight our triangle here. Okay. So now let's determine all of our variables. A. This is the height of the ladder. So from the floor to the top, it says 15 feet above the ground. So A is going to be our 15. dA dt is how fast the top of the ladder is sliding down. And it tells us the top of the ladder is sliding down the wall at a constant rate of 3 feet per second. So it's the rate that the height is changing is -3. So it's the height is getting smaller, so it's a negative, and it tells us it's at 3 feet per second. B is the distance the bottom of the ladder is away from the wall. And that one we are not given. And it is asking us how fast is the bottom of the ladder sliding away from the wall. So we also don't know that one either. C is how long the ladder is. We're told it's a 30-foot ladder. So C is 30. And is the length, how fast is the length of the ladder changing? Well, the ladder is not changing. It's a 30-foot ladder. It's just falling down. So the rate that the length of the ladder is changing is 0. It's not changing at all. Okay, so we have A and we have C. We can find B using our Pythagorean theorem. A squared plus B squared equals C squared. A is 15 and C is 30. So B squared equals 900 minus 15 times 15. Yeah, 225. I just like to double check. Okay. B squared equals 675. So if we take the square root, our B is going to be approximately 25.98. So let's update what we know. And now, let's solve for dB dt. So I'm going to continue using my Pythagorean theorem for the same reason we used it in the last example. I want to have A, B, and C, and I want to have dA dt, dB dt, and dC dt. Most importantly, we want a formula that's going to give us dB dt, since that's the one we're looking for. So the derivative of A squared, 2A dA dt, derivative of B squared, 2B dB dt, derivative of C squared, 2C dC dt. Let's fill in what we know. 2, A is 15, dA dt is -3, plus 2, B is 25.98. We don't know dB dt. 2, C is 30, and dC dt is 0. So this zeroes out. Over here, we will have 51.96 dB dt, and then -90. We'll move the 90. And then we'll divide by our 51.96. Which should give us dB dt approximately 1.73. So the bottom of the ladder is sliding away from the wall at about 1.73 feet per second. Okay, the radius of a spherical balloon is increasing at a constant rate of 5 inches per minute. How fast is the volume changing when the radius is 15 inches? So we have a balloon. It's as spherical as we can make it. And we are pumping air into it. So it's getting bigger and it's getting more volume, taking up more space, right? So it looks like we're going to have really two variables, because let's think about the volume of the balloon. So I'm going to kind of put a circle around it, right? It's a circular balloon, which I don't think I've ever seen a circle balloon, but we can imagine. If we were to calculate the volume, think back, what is the volume of a sphere? 4/3 pi r cubed. So the important variables here are the volume and the radius. And both of these things change as our balloon gets bigger. So let's outline our volume, our radius, and then the rate that these things are changing, dV dt and dr dt. So the radius of a spherical balloon is increasing at a constant rate of 5 inches per minute. So our radius is changing at 5 inches per minute. That's our rate. That's our dr dt. How fast is the volume changing? So we don't know dV dt when the radius is 15 inches. So our r is 15. We also don't have v. But thanks to our equation, we can find what v is. So let's do that first. Our volume, 4/3 pi. The r we're looking at is 15 cubed. So if we multiply this 4/3 times 15 cubed and leave the pi in so that way it's as accurate as possible, we should be getting 4,500 pi as our volume. And that's how I'm going to leave it for now, just so that way we're not approximating too early. So we'll update what we know. And now we can make an attempt to answer our question. How fast is the volume changing? So we'll continue to use our formula. V equals 4/3 pi r cubed. Let's take the derivative. So derivative of v will be dv dt. Here we have our variable is r cubed. 4/3 pi will be our constant, so you can pull your 4/3 pi out front, take the derivative of r cubed, so we'll have 3r squared, and then chain rule, dr dt. Okay, so let's clean this up a little before we plug in dv dt, 3 divided by 3, so we will have 4 pi r squared dr dt. Let's plug in what we know. dv dt is our unknown. 4 pi r is 15 squared. dr dt is 5. So we have 4 times 15 times 15 times 5. We've seen this before, haven't we? dv dt is going to give us the 4,500 pi, which is approximately 14,137. And so the volume of the balloon is increasing by about 14,137 cubic inches per minute.